Asteroid Bennu, a celestial enigma, is more than just a rock floating in space. It's a time capsule, a witness to the birth and evolution of our solar system. This asteroid, a subject of NASA's OSIRIS-REx mission, has revealed an extraordinary story through the analysis of its samples. But here's where it gets controversial. Bennu's origins are not as straightforward as one might think. It's a mixture of materials from various corners of the solar system and even beyond. Imagine a cosmic melting pot where fragments from a larger asteroid, shattered by collisions, came together to form Bennu. And this is the part most people miss. The parent asteroid of Bennu was a diverse collection of materials, some from near the sun, others from distant regions, and even remnants of other stars. This cosmic blend coalesced over 4 billion years ago, during the formation of our solar system. The findings, published in Nature Astronomy, suggest that Bennu's parent asteroid might have formed in the outer regions of the solar system, possibly beyond the giants Jupiter and Saturn. We think this parent body was struck, shattered, and reassembled multiple times, says Jessica Barnes, an associate professor at the University of Arizona's Lunar and Planetary Laboratory. By studying the samples returned by OSIRIS-REx, Barnes and her team have pieced together Bennu's history. They've discovered an abundance of stardust, material that predates our solar system, and organic matter that likely formed in interstellar space. The NanoSIMS instrument at the Kuiper, Arizona laboratory played a crucial role in identifying these ancient materials by analyzing their unique isotopic signatures at nanoscale levels. These are pieces of stardust from long-dead stars, incorporated into the gas and dust cloud that gave birth to our solar system, Barnes explains. The chemical and isotopic similarities between Bennu and Ryugu, another asteroid sampled by Japan's Hayabusa 2 mission, as well as the most primitive meteorites found on Earth, suggest a shared region of formation in the early solar system. However, the differences observed in Bennu's samples might indicate that the starting materials in this region were not as well mixed as previously thought, or that they changed over time. The analyses show that some materials in the parent asteroid survived various chemical processes involving heat and water, even the collision that formed Bennu. But most were transformed by hydrothermal processes, with minerals likely forming, dissolving, and reforming over time due to water interactions. Bennu's parent asteroid likely accreted a lot of icy material from the outer solar system, which melted over time, says Tom Zega, director of the Kuiper, Arizona laboratory. The team found evidence of silicate minerals reacting with liquid water at room temperature, possibly due to lingering heat from the accretion process or from later impacts and radioactive decay. The water reacted with the minerals, creating samples with 80% of minerals containing water in their interior, a legacy of the solar system's formation billions of years ago, Zega adds. But Bennu's story doesn't end there. A third paper, also published in Nature Geoscience, reports microscopic craters and tiny splashes of once molten rock on Bennu particles, signs of micrometeorite impacts and solar wind effects, known as space weathering, error code 502.